Hi everyone. Today let's talk about the last session of this chapter, 8.6, Alternating Series. Big idea. If the terms of a series go to 0 and they alternate sign, then the series converges. If a series has some negative terms, but the terms do not necessarily alternate in sign, and the series of the absolute value of a sub k converges, then the series a sub k will converge because those occasionally negative terms will cancel some of the positive terms. Thus, we get the overall convergence. The idea is like the series of the absolute value is like the big guy. The series of the AK is like a small guy. So if the big guy converges, the small guy also converges. Okay, so we'll talk about more. Big skills. You should be able to recognize an alternating series and know when it converges. You should be able to show when a series converges absolutely. Okay, so we'll talk about all of these in this session. First of all, let's talk about the definition of an alternating series. An alternating series is a series whose terms alternate between positive and negative. So you can look at this guy. So you can see the formula. It contains the factor -1 to the k plus 1. Okay, so you can see the first term is positive, the second term is negative, the third term is positive, and the fourth term is negative. So the sign alternates. So this is an alternating series. Okay. Sometimes you may see this factor is like maybe -1 to the k instead of k plus 1. It really depends on whether the first term, whether it's positive or negative, and what's your index. Does your index start with 1 or start with 0? Okay. So if a series, the sign alternates between positive and negative, then this is the alternating series. For alternating series, we have an alternating series test. Okay, an alternating series converges if the following two conditions are satisfied. First, the terms are non-increasing in magnitude. So non-increasing, so it's either stay the same or less than that. Okay, for some big index, so after a big index. So we talk about whether a series converge or diverge, we care about the tail. Maybe for the first couple of terms, it does not satisfy this condition, but as long as eventually it satisfies the terms are non-increasing, then we're good. Okay, and the second condition is the limit of a sub k goes to 0. Okay, so if I draw a picture here, okay, then the series looks like, so if we draw, the series looks like, maybe it's the first point here, the next one is negative, and the first point is positive and negative, positive, negative, okay? As long as the terms are non-increasing in magnitude. So you can see it's like smaller, smaller, okay? And you can see the limit is getting close to 0, okay? As long as the alternate series satisfies those two conditions, then we know it converges, okay? So this is the alternating series test. Here is an example, the alternating harmonic series. The alternating harmonic series, this is -1 to the k plus 1 over k. So it actually equals to 1 minus half plus 1/3 minus 1/4. So this alternating series actually converges. Even though the harmonic series, which is sum of 1 over k, this series diverges. Why the harmonic series diverges? If you can remember the p-test. So this guy converges if p greater than 1, and it diverges if p less than or equal to 1. So when p equals to 1, that's the harmonic series, so we know it diverges. But however, the alternating series, so let's check those conditions. Okay, so let's look at the alternating harmonic series. The first conditions are the series non-increasing. Yes, actually the terms 1 over k is decreasing. It's not only non-increasing, it's decreasing, right? And second, you can see the limit k goes to infinity, 1 over k is 0. So it satisfies the two conditions of the alternating series test. So that's why by the alternating series test, the alternating series converges. Okay, so this is an example that the harmonic series diverges, but the alternating harmonic series converges. Okay, and next we're going to talk about very powerful theorem and definitions. So a series sum of a sub k, okay, is said to converge absolutely if the series of the absolute values converges. It is said to converge conditionally if the series converge, but the series of the absolute values of the terms diverges. Okay, so you can see the series of absolute value. Okay, so let's see here. You can see the series of absolute value of a sub k. This guy is greater or equal than the series of a sub k, right? Because the absolute value, when you add them all up, is positive. But however, the series, some terms might be positive, some terms might be negative. So that's why if we just look at the magnitude, the series of the absolute value of a sub k is actually bigger than the magnitude of the series of a sub k. Okay, everybody? So that's why you can think of this is the big guy and this is the small guy. So that's why if we know the big guy converges, that implies the small guy also converges. Right, everybody? So that's why if a series of the absolute value of the a sub k converges, the series itself must converge. And this is said to be converge absolutely. Okay, so let me write it here. So converge absolutely means both series of a sub k and the series converges. And converge conditionally means the series itself converges, but the series of the absolute value of a sub k diverges. Okay, so this is like the small guy converge, but the big guy diverge. So far, so good, everybody? So that's why we have the absolute convergence implies convergence. If the big guy converges, then the small guy converges. If the small guy diverges, then the big guy diverges. So this concept is very similar to the comparison test we learned before. Okay, so it's not something new. Okay, it's like we apply the comparison test to this series and the series of the absolute values of the terms. Okay, everybody? So keep this in mind. But before we go over examples of the alternating series, I hope that you have realized all the previous problems of this chapter. The problem is like determining whether the following series converges or diverges. But when the problems give us an alternating series, then the question is determine the following series converges absolutely, converges conditionally, or diverge. So here we have three, 1, 2, 3. So we have 3 possibilities. Converge absolutely, converge conditionally, or diverge. So that's why I want to show you this map. So this map is summarized what we have learned in chapter 8. Okay, so let's look at it. Let me make it smaller. Okay. So given a series, all the terms are positive, okay? So given a series, we want to ask whether the series converges or diverges. So here is like we have 2 possibilities, either converge or diverge. What are the steps? Step 1, we compute the limits of the sequence. Does that equal 0? If no, then the series diverges by divergence test. If yes, if the limit of sequence equal to 0, we go to step 2. Okay, and we look at the terms a sub k. First questions, are these special series? Is this a telescoping series? If yes, then we express as a difference between 2 terms. And then we compute the first nth partial sum. And then we can cancel many terms. We will get a formula of n. And then we let n goes to infinity. That's the limit of the series. Okay? So that's the telescoping series. Second, geometric series. Does the series look like sum of a r to the k? Okay, so maybe it does not look exactly like that. Maybe there is a way that you can group all the factors under the k together, and that's our ratio r. Okay, and depending on the absolute value of the r, if that is greater or equal to 1, then the series diverges. If the absolute value of the ratio is less than 1, then the series converges to first term over 1 minus the ratio. Okay, because I don't want you to use this formula because sometimes if your k does not start with 0, then it's not necessary the a. So I hope that you can remember that is the first term. That is the first term over 1 minus the ratio. Okay? And then another special series is the p series. So it looks like series of 1 over k to the p. And if p less than or equal to 1, the series diverges. If p greater than 1, then the series converges. Okay, and then next, integral test. Does a sub k looks like an integrable function? I.e., usually if you can see there are some factor is the derivative of some other term, well then think about integral test because you can solve the integral by u substitution. So for example, this problem, you can see 1 over k is the derivative of ln of k. Okay, if k is a variable. Alright, so to use integral test, we have to check the hypothesis is satisfied. So that is the function f. We replace k by x. F of x is continuous, positive, and decreasing. Okay, if you check all those 3 conditions, then you can compute the integral from 1 to infinity. Okay, does this guy converges? Is this guy finite? If it's finite, yes, then the series also converges. If this integral is infinite, okay, then no, the series diverges. Okay, that's the integral test. How about ratio test? The ratio test, a sub k, usually you can see it has terms k to the factorial, a to the k, k to the k. Okay, so here I want to review the growth rate sequence with you. The slowest is ln of k, and then we have k to the p, and then we have exponential function, and then we have k factorial. The fastest is k to the k. Okay, so you can use this to see whether the numerator is bigger or the denominator is bigger. Then you can conclude whether the limit of the quotient is 0 or infinity. Okay, and then when you apply ratio test, you compute R. The ratio is the limits of a sub k plus 1 over a sub k. So absolute value of that. The series converges if R less than 1. And it diverges if R greater than 1. And it's inconclusive if R equals to 1. Okay, so actually from R, because it's the limits of the absolute value, we already know R is greater or equal to 0. Okay, and then root test. When do we use the root test? Well, that is when your a sub k looks like everything to the power of k. Because the root test is going to take the k roots. So if everything is to the power of k, when you take the k roots, they kind of cancel. And then you get easier problem, the limits you can solve. So similar criterion, if q is less than 1, the series converges. If q greater than 1, the series diverges. If q equals to 1, it means you used the wrong test. Try other test. Okay, and then we'll talk about the comparison test and limit comparison test. So I strongly recommend you to use the limits comparison test. When do you use the limit comparison test? If your series is comparable to a p-series. So this is the common use. If you look like, oh, we have a complicated series, but when k goes to infinity, we can just look at its dominant terms. So the dominant terms is like a k-series, a p-series, sorry. Okay, and then L is the limit of a sub k over b sub k. So b sub k is the series we know whether it converges or diverges and we want to compare with. Okay, so in this case, most of the case you compare with the p series. So usually, if you get the p series by looking at the dominant terms of the numerator and denominator of your a sub k, then this limit should be 1. Usually, if this is how you get your p series, don't forget you might have some coefficient in front of it. Okay, so and then usually your L will be 1 if that is how you get your p series, by looking at the dominant terms of the numerator and the dominant terms of the denominators of a sub k. If L is 1 or any number, okay, it's not necessary to be 1. It means it is a finite number. Okay, a finite number which is not 0. Then a series, both series, either both converges or both diverges. Okay, if L is not a finite number, not equal to 0, so if L equals to 0, oops, sorry. Okay. Alright, yeah, sometimes I touch my keyboards. Okay, so if L is 0 or infinity, then just remember the big guy converges implies the small guy converges. The small guy diverges implies the big guy diverges. Okay? That is for the series. Given a series, we can talk about whether it converges or diverges. But how about in this session, when we're given an alternating series, then we have 3 possibilities. It either diverges or converges absolutely or converges conditionally. So it's like you're playing a game, right? Before, it's like the possibility is you either save the princess or you fail to save the princess, right? So that was this page. You either save the princess, okay, or fail to save the princess. Okay, but Right now, we have 3 conditions. So this looks like, oh, you either fail to save the princess. Here, you save the princess, and the princess wants to be your girlfriend. Okay? And here you save the princess, but the princess doesn't want to be your girlfriend. Okay? So here are the 3 possibilities. So we have diverges, or converge absolutely, or converge conditionally. Alright, let's look at the steps. First step is still the same. We compute the limits of the sequence. Does that equal 0? If no, diverges by divergence test. If yes, go to step 2. Step 2. So you can see this is an alternating series. So step 2 is you forget about the alternating sign. Forget about the -1 to the k. Okay, so this series, all the terms are positive. Okay, does this guy converge? Well, here, this is, you use the techniques we learned in last page. Okay, like previous. Is it a special series? Can you use the integral test? Can you use ratio, roots, and limit comparison tests? If this series converges, then you would say the alternating series converges absolutely, because if this series converges, it also implies the alternating series converges. Remember, this is the big guy, the series is the big guy, and then the alternating series is the small guy. So if the big guy converges, the small guy also converge. So in this case, both of the series converges, then we say the alternating series converges absolutely. Okay, so if the series of AK diverges, go to step 3. Okay, then usually you realize the A sub k is decreasing. Okay, and because by step 1, we proved that the limit of A sub k is 0. So the series looks like that. Okay, alternating, maybe it's switch back and forth. But because the limit is going to 0, and so if you just look at the terms, the absolute value of the terms is actually non-increasing. So by the alternating series test, the alternating series converges. So we have the series diverges, but the alternating series converges. So that's why we say the alternating series converges conditionally. So far, so good, everybody? So keep in mind those 3 steps. Let's work on our examples. Okay. Example 1. A sub k, what is A sub k? So this guy is A sub k. So A sub k does not include the -1 to the k. However, you gotta be careful. So if you see -2 to the k, what do? You're gonna split it. You split it as -1 to the k and 2 to the k. So when you talk about A sub k, you gotta include the 2 to the k. You don't include the -1 to the k, but you should include 2 to the k. Okay? So our first step is to compute the limits of the sequence. So ln of k to the 2/5 over k. Well, ln and k, which one grows faster? Well, the polynomial grow faster, right? The power function grow faster. So that's why if the denominator grow faster, well, then this quotient is 0. Okay, that means divergence test does not work here. So it tells us nothing. Let's go to step 2. Well, step 2, we want to ask whether the series of A sub k converges. Okay, and let's look at the series. Well, the series is ln of k, and can you see there's 1 over k in the this term, and 1 over k is the derivative of ln of k. So we realize this is an integrable function. So we use integral test. So that's why first we're gonna define f of x. That is, replace k by x. So we mentioned this is continuous, positive, and decreasing. Okay, and then we compute the integral. So our integral from 2 to infinity, because the k starts with 2, of ln of x to the 2/5 over x dx. Well, we can use u substitution and let u be ln of x, right? All right, then we can also see this is improper integral. We replace it by t. Okay, so now we have the integral of u to the 2/5 du. U to the 2/5, the integral is what? U to the, we add 1 to it. Okay, we know it's u. Okay, so u is ln of x. We add 1 to it, becomes 7/5. So divided by 7, multiplied by 5. Now evaluate from 2 to t. Well, you see this process, I'm using u substitution in my mind, right? I know u is ln of x, du is 1 over x dx, then this guy is like u to the 2/5 du, so the integral is u to the 7/5 over 7 times 5. And then I put the u back, u is ln of x, right? Okay, so that is, we plug in t first. Minus, we plug in 2. Okay, what happened? Can you see that the ln of t, when t goes to infinity, this guy also goes to infinity. So the answer is infinity. Oh, so we know the series a sub k diverges. So if it diverges, it means we go to step 3. Okay, so step 3, we use the alternating series test. So we have to verify the alternating series test the hypothesis of that. So a sub k is decreasing. Is it decreasing? Yes, because k is bigger. It grows faster than ln of k. So the denominator is bigger, so a sub k is decreasing. And also, because in the first step, we already showed the limit is 1. So we can use by alternating series test, our alternating series converges. Okay, so because the series of a sub k diverges, but the series of the alternating series converges. So that's why we have the alternating series converges conditionally. Okay, everybody? So this is the complete process of solutions of this problem. So ideally, if you stop at step 1, then your conclusion will be diverges by divergence test. If you stop at step 2, you will get converges absolutely, because you get the series of the absolute value of a sub k converges, so we get converge absolutely. If you go to step 3, your conclusion will always be converges conditionally. Okay, everybody? So let's continue to work on more examples. All right, let's look at this one. So this one, so I hope you can pause here and try to work on this problem first before we continue. So this is a sub k. All right, so this is a sub k. We first compute the limits of the sequence. Well, the limit of the sequence, let's see. What is the dominant terms of the numerator? So you can see the dominant term of the numerator is k to the 4th. And what's the dominant term of the denominator? 5k to the 4th, right? Yeah, so sine, cosine, they're bounded between -1 and 1. So dominant terms are k to the 4th and 5k to the 4th. So we get limits k goes to infinity, k to the 4th over 5k to the 4th. Oh, what happened? The answer is 1/5. 1/5 is now 0. So we say the series diverges by the divergence test. And we can stop here. So I think this is the easiest case. You just compute the first steps, you get the limits of the sequence is not 0, then it just diverges by divergence test. We can stop here. Yes. Alright, so let's continue. So example 2. We want to determine whether the following series converges absolutely, conditionally, or diverges. Okay, so let's follow the 3 steps. First, so this is my a sub k. Okay, so what's the limit of a sub k? Well, let's look at the dominant terms. What's the dominant terms of numerator? Square root of 9k to the 5th. Square root of 9 is 3, and then we have k to the 5/2. How about dominant term of denominator? We have 13k times square root of 64k to the 4th, right? So these are the dominant terms. Okay, so 13k, square root of that is 8k squared. Right, everybody? So what do we get? We get 13 times 8k cubed. Alright, so what's the limits? We have the numerator 3k to the 5/2 over 13 times 8k cubed. Okay, what is that? Well, we can see that's the limit. K goes to infinity. We can group the coefficient together. So 3 and 13 times 8 down there together. K cubed and k to the 5/2. Which one is bigger? So 3 is like 6 over 2. So the denominator is bigger. So we get 3 minus 5/2. So we combine the k together. Because we know this is a p series and we have to figure out what's the p. Okay, so we get 1 over, so this is k to the, actually 1/2. So because the numerator is a constant, the denominator is k to the, it has a factor k to the 1/2. When k goes to infinity, this guy is 0. So far, so good, everybody? Alright, because of 0, divergence test tells us nothing. We can go to the step 2. So what is step 2? So step 2, we compute the series of a sub k. Okay, we compute the series of a sub k. Here, because you see the series is comparable to a p series, what test we should use? Yes, use limit comparison test. Oh, let me see. The last example, did we mention integral test? We did not. So we should mention by integral test. Okay. So I think it's good to, after you figure out which test you use, you put it right there, just in case later on you forget to mention that. Okay? So we use a limit comparison test. So L is the limit. K goes to infinity of a sub k over our p series is 3 over, what's 13 times 8? So 13 times 8 is 104. And then we have k to the 1/2 down there. And that is 1. Because how do we get our p series? It's by looking at the dominant terms of the numerator and denominators of the a sub k. So that's why eventually they behave like the same. Okay, so that's L. Because L is a number, not 0, not infinity. Then we know both series, they either both converge or both diverge. So by the p series, by the p test. So by the p test, our p series 3/104 k to the 1/2. So p is 1/2. 1/2 less than 1, so it diverges. Then by limit comparison test, our series also diverges. Okay, so here you have to mention which series do you mean? So you cannot just say, oh, series diverges. What do you mean? Which series do you mean? Okay, so specify. You can say series of a sub k if you don't want to copy the whole problem like that again, right? Okay, but you have to tell me which one. Okay, so when we go to step 3, we always say a sub k is decreasing, and it is. Eventually, okay, maybe the first couple of terms is not decreasing, but eventually it will is decreasing. Okay, and we already showed that the limits of a sub k is 0 in the first set. So by the alternating series test, so here this is -1 to the k plus 1 because our problem is to the power of k plus 1, so we copy that down. So the alternating series converges. So because we have the alternating series converges, but the series of a sub k diverges. So that's why we answer the alternating series converges conditionally. So far, so good, everybody? That is example 2, part A. Let's continue. So let's look at part B. Okay, so I hope that you can pause here and try to work on part B. Okay? Are you done? Let's check our work. So this is a sub k. First, limit k goes to infinity of a sub k equals to, let's look at the dominant terms. Well, that's our dominant terms. So let's split the coefficients and the powers of k. So this is k root of 2. And this is k to the 7/3, right? How about the dominant term of denominator? Square root of 4, and then k to the 5/2. So far, so good, everybody? So we get limits k goes to infinity of k root of 2, square root of 4, which is 2. And then we have k to the 7/3 over k to the 5/2. So 7/3 and 5/2, which one is bigger? It's actually 5/2 is bigger. Okay, and cube root of 2 and a 2 you can cancel. You get 2 to the 2/3. Okay, because it's like 2 to the 1 minus 1/3 is 2/3. Then we have k to the 5/2 minus 7/3. Okay, what is that? Well, 5/2 minus 7/3, we take the common denominator 6. 3 times 5, 15. 2 times 7, 14. So that's 1/6. So this guy we have 2 to the 2/3, k to the 1/6. And we have this guy, the limit goes to 0, right? That is the first step. Well, the second step, we want to figure out whether the series a sub k converges or diverges. And because this problem we can compare to a p-series, so we use limit comparison test. So L is the limit of a sub k over our series, which is 2 to the 2/3, k to the 1/6. And that's 1. Because this is how we get our p-series, by looking at the dominant terms of the numerator and denominators of a sub k. So they behave the same eventually. Okay, and let's see, by the p-test, our p-series, so k is 1/6. 1/6 is less than 1. Less than 1, the series diverges. And then by the limit comparison test, our series also diverges. That means we gotta go to step 3. So step 3, we say a sub k is decreasing. And because we already showed the limits of a sub k is 0 in the first step, so we can say by the alternating series test, our alternating series converges. So eventually you will get what? The alternating series converges conditionally. Okay, so don't forget to put the sum, okay? Alright. We mean the series converges conditionally. Alright, so that is example 3. Okay, next. So first of all, let's look at our a sub k. This is a sub k. Have you finished this problem? Okay, let's continue and check our work. So when k goes to infinity, okay, do you know what is arctangent of k? So arctangent of k, well, we look at the graph of tangent. So arctangent of k means when we look at the function's tangent x, the graph of tangent x, when the y value goes to infinity, what's the x values? So that is actually pi over 2. Okay, so eventually it looks like pi over 2 over k cubed. So that's why this guy is 0. So far so good, everybody? So this is like a p-series. So like a p-series, so that's why step 2, we want to talk about whether the series a sub k converges or diverges. Alright, so what test do we use here? Do you remember? If we can compare to a p-series, what test we can use? We use limit comparison test, right? Alright, so let's see. We use limit comparison test. So we compute L. So L is the limits k goes to infinity of a sub k over our p series. Well, I can combine the 2 and k cubed together. Okay, this is 1 because they behave very similar at the eventually, right? So by the p test, our p series converges or diverges. Because p is 3 is greater than 1, so this is actually converges. Then by the limit comparison test, our series converges. Yay! So we can stop here, and because the series of a sub k converges, then we say the alternating series converges absolutely. Okay, so that is our conclusion. And so this is part C.